Okay, this is your second video. These concepts are a little more abstract and they kind of bleed together, so um, this may be something you want to look up in your AP study guide or on the internet or in your textbook or one of the other resources you have, just to make sure you understand what's going on. This is electric potential and electric potential energy. We're actually going to start with electric potential energy. So you remember work and power and energy. Work was force times distance, power was energy over time, and energy was all kinds of different things. Objects have potential energy because their positions change though. So you remember, if I gave you an object that was here, you know that as the object reduces its height because of its position, it would lose some of its energy because potential energy was m times g times h. So in this case, charge in an electric field, now this is an object here, this is an object in a gravitational field, and fields are very similar. So now instead of an object on a hill changing its position in a gravitational field, we have an object, a much smaller one with a charge, that has potential energy because of its position in an electric field. So since there is a force, remember K, Q1, Q2 over R squared, on the charge, and it does work against this force, we can say that it must have energy for doing work. In other words, we can say that energy required increasing the distance between two charges to infinity or vice versa. Electric potential energy is scalar. Remember, energy doesn't have a direction. You can't have West energy. And joule is the unit of it. Now I'm going to use EPE when I notate electric potential energy. Now what that means is, you remember way back when work was force times distance. Well, if I have a positive charge, and let's say I nail it to the board here, it can't move. If I want to bring another positive charge some distance d or x, I need to exert a force on it in that direction. Well, if you exert a force over a distance, you're doing work. And that's exactly what electric potential energy is. You can see the equation over here is EPE equals KQ1 Q2 over D. Once again, I am going to use R for this. Okay, so it looks very similar to Coulomb's law, but there's no absolute values, and it's not over R squared. This is a direct relationship. Just like potential energy over here was a direct relationship. 1/2 the height is 1/2 the potential. Over here, the same thing applies. In this formula, if the charges have an opposite sign, then electric potential energy becomes negative. If they are the same, then it becomes positive, and that makes sense. So electric potential energy is equal to K Q1 Q2 over R. Now that makes sense. If both of these were negative, electric potential energy would be positive. If both of these were positive, the same thing would happen. And if they're opposite charges, then electric potential energy becomes negative. The second note says, if electric potential energy is positive, then electric potential energy is inversely proportional to the distance d. Okay, so, and that's unfortunately just confusing to word, but we'll make this bearable. If this is positive, electric potential energy will do what if R increases? Well, if I double R, that's the same as multiplying this whole side by 1/2, by the way. I have to do the same thing over here. So, is inversely proportional to R. As R increases, electric potential energy decreases. And that makes sense. Because if I have a positive charge right here and a positive charge right here, it has more energy than if I took this same positive charge and moved it twice as far. 1/2 the energy, 1/3 of the energy, but it's inversely proportional. The next one says, let me put some parentheses around this. If the electric potential energy is negative, the electric potential energy is directly proportional. So what that means is if this is negative, EPE is directly proportional to R. So now instead of having a plus charge and a plus charge, the only way to have opposite charges would be to have a plus charge and a minus charge. Now think about it. As I move this minus charge closer, what would happen to the energy between them? Well, as R goes down, the energy will go up. I'm sorry, down also. The energy will go down. They're directly proportional. Because it takes, how much work do you think how much do you have to force this charge to move? It wants to do it anyway. It's a positive and a negative. So as this thing gets closer, the amount of energy needed to get them even closer drops also. So they are the same. If R goes up, if I move this charge way far away, if I move that charge way far away, now I have to exert more force to get them together because they're not as close and they don't want to do it on their own as much. Just a couple examples. In Figure 1 and Figure 2, the charges repel each other. Thus, external force does work for decreasing the distance between them. What that means is, if I want to move this charge, if I want to move it closer, I have to do work. And because they are both positive, I have to use a lot of force. But if you look at Figure 3, the charges attract each other. The distance between them is decreased by force. And therefore, I don't have to push at all. This thing will move all by itself. And that's what I mean by directly and indirectly proportional. Now, we're going to go through this example fairly quickly because it's pretty basic. If you have three charges, 10Q, 8Q, and negative 5Q, and they're in a right triangle separated by whatever distances, and I ask you to find the total energy of the system, all you do is find the energy between each one. This is the energy between 1 and 3, using the equation KQ1, Q2 over R. This is the energy between, I'm sorry, this was 1 and 2. This is 1 and 3, and then this would be 2 and 3. And then after you find each one, you just bring it down. And you add them all up. And once you find common denominators and everything like that, you find your final answer right here. Okay, so it's a nice, easy quantity. There's not going to be any angles or anything like that, which is nice. You're just adding up energy. Okay, we're going to start the next thing. This is electric potential. I think this is a little more confusing, but we'll try to get you through it. It says electric potential is the electric potential energy per unit charge. It is known as voltage. So finally, you've heard of something. Voltage is often used in batteries and things like that, and we will be using it for circuits, but it means something beyond that. So in general, not in general, in here, voltage is going to be symbolized by a capital V, and the units are volts, which are symbolized by a capital V. So that's fairly easy, just like volume. Okay, so this is essentially, this is electric potential energy, which you remember, because it was just a couple minutes ago, is K, Q1, Q2 over R. Okay, K, Q1, Q2 over R. Well, if you take this equation and you want to know how much energy something has per coulomb, per charge, you divide the whole thing by Q. Well, if you divide the whole thing by Q, and it becomes voltage, which is just K, Q over R. By the way, you're also going to see capital Q. It means the same thing. There's no difference between capital and lowercase q. So let's see here. We'll take a look at this picture. So if you look at this picture, this is an infinite distance. Now don't be confused or put off by the infinite thing. It just means you're taking it from a really long ways away to a really close position. That's all the infinite thing means. So it says 1 coulomb of charge is brought to point A from infinity. So it's brought from here to there. Work done here is called potential of Q at A. Don't worry about the notation. Electric potential is found with the given formula, which we have over here already derived. Voltage, once again, you're lucky. There will be no angles or anything like that. It is a scalar, so you just add them up, 1 plus 6 plus 4. If Q is negative, then V is negative. If Q is positive, then V is positive. That's it. Since there can never be a negative K, there can never be a negative Q, there can never be a negative R. Oh, wait, sorry, there can be a negative Q. This can only be positive because it's a given. There's no such thing as a negative distance. And that can be negative or positive. So it's very simple. If Q is negative, then voltage is negative. If Q is positive, then voltage is positive. And remember, voltage is the same as electric potential. Okay, potential difference between 2 points. Work done against to the electric field. Work done against the electric field to move unit charge from one point to another is called potential difference. Now, there's no zero, just like there is no actual, let's see here, remember when we did this? We would set that equal to 0 wherever we really saw fit, because we were able to control the problem. The same sort of thing applies. There's nowhere in the universe that we have found or know of where there is no potential naturally. So what we do is we tend to not look for the electric potential at one point. We look for something called potential difference. And the potential difference is very easy. Anytime you see a potential difference, it's simply final minus initial, just like it always has been. This difference is found by the differences of potential. So if we take a point charge from A to B, so here we go, this Q is nailed to the board. So we're moving this charge to point B. Close, I guess. Well, that's going to annoy me. Then the potential difference is simply by taking final, which is the voltage at point B, minus initial. That's it. And you notice here it says W. Remember, work is electric potential energy. They're both measured in joules, therefore they must be the same thing. A very quick example, it says find the potential difference between points A and B in terms of K, Q, and R. Well, at least we're using R again. All right, brought the picture over. So if I want to find the potential between A and B, I simply take the potential at A, which is right here, KQ over R, and this is my charge. This is whatever my Q is right here. I do the potential at B, which is KQ over 2R, and I take my final, which is B, minus my initial, which is A. Now this looks confusing, but this is just finding the common denominator between 3 and 2. The only way to turn these things together, to add them up, is to have common denominators. So make sure you remember how to do that. And you just end up with KQ over 6R. That's really it. You just add them together or subtract them depending on their sign. And that's how you do it.